All right, welcome to random variables in the normal distribution. First of all, let's talk about what a random variable is. A random variable is a variable whose values are determined by chance. There's two types of them, discrete and continuous random variables. Discrete random variables are like the number of tattoos someone has. Well, if we had a sample of human beings and we counted the number of tattoos that someone has, that would be a discrete random variable. A continuous random variable is something we can't count. There's infinitely many values. There's a best way to be described there is a number line. So if I just drew this line, a straightish line, and marked the numbers 1 and 2, there's actually an infinite amount of values between 1 and 2. I can subdivide this. I can subdivide it again. And I can keep going. And I can keep doing that infinitely. Okay, so that's what I mean by can't be counted. You can't count the numbers between 1 and 2. Probability distributions. This is where our discussion will be going, and we'll be talking about this a lot. Mostly in the continuous random variable world. Discrete random variables, not so much. Probability distribution of a discrete random variable provides all the possible values that the random variable can assume, together with the probability associated with each value. The probability distribution can take the form of a table, graph, or formula, and probability distributions describe populations, not samples. So if we were going to talk about a probability distribution, the sum of the probabilities of all the possible values of a discrete random variable must equal 1. Okay, so we're talking decimals and fractions, so they're all going to equal 1. I don't know if I've talked about this symbol yet. This is sigma. This just means added up, so it means sum. The probability of each value of x must be between 0 and 1 inclusive, so it's always got to be between 0 and 1. We're talking fractions and decimals. So let's look at an example. So when I say page 262 in the book, I mean in the second edition. This is the first time I've used the third edition of Discovering Statistics. So when I refer to things in the book, you may not actually see it in your textbook, or be in the same place as your textbook. So let's look at constructing a probability distribution table for the number of heads observed when tossing a fair coin twice. So if I tossed a coin, I got heads and heads. Why are we erasing as I write? I got heads and tails. I got tails and heads. And then I got tails and tails. That is so weird, guys. Sorry. I have a small dead spot on my tablet, and I think that's the problem right here. There we go. Okay. So the probability of finding no heads was 1 in 4 because we had our tails and tails option. The probability of finding 1 head was 1/2 because we had 2 out of the 4 options. And then the probability of finding 2 heads was down to 1/4 because that was only one of the options. So that's what I mean when we're talking about a discrete random variable. However, not however, sorry. When we're talking about discrete random variable, we're talking about mean and variability of a discrete random variable. So, or expected value. So the best way to explain expected value is I invested in a biotech company. This is, again, page 263, probably from the second edition of Discovering Statistics, so you might not actually find it. So you invest in biotech, and if you get and it does well, you get a financial gain of $1,000, and the probability of that happening is 0.15. Biotech does fairly well, and that's $500. The probability there is 0.3. Biotech treads water, neither here nor there. You just stay the course, and that's 0.25. Biotech does not do well, and that's $200 of a loss, and that's a 0.2 chance of happening. And then if the company folds, you lose $2,000, and you have a 0.1 chance of that happening. So what you're going to do here is you're going to find the mean or the expected value of this problem. So we go 1,000 times 0.15, 500 times 0.3, 0 times 0.25, and negative 2,000 times 0.1. And then you're going to add all of that up. And you're going to get your expected value of investing in this company over time. So, I'm going to call up a calculator. Do I have a calculator on here? No. Where's my calculator? Thank you. Sorry, I'm rambling to myself. So if we've got 1,000 times 0.15 plus 500 times 0.3 plus negative... Oh, I skipped one. I completely forgot the negative 200 times the 0.2% chance of happening. It's in there. So let's get that calculator up and running again. Clear. So we got 1,000 times 0.15. That's 150. I'll add all these up in a second. And then we got 500 times 0.3. That's 150. Zero times 0.25 is 0. 200 times 0.2, that's negative 40. And then 2,000 times 0.1, that's negative $200. So 300 minus 240 is $60 total. That is your expected value for this problem. So that's what expected value means there. There's no exact formula to calculate this in Excel, but you can use Excel or Sheets to do it. So what I'm going to do is I'm going to show you in Excel. Give me 1 second. I'm going to pause the video and get that set up. And magically, we have an Excel sheet with the values and the probabilities laid out. So to use Excel or Sheets, the coding is the same. I'm going to press equals to let the system know that I'm going to do math. And I'm going to select the value times the probability. And then I'm going to drag it down so I get everybody's. And then I'm going to ask it to equal sum, parentheses, of all of these guys. And boom, $60. Got the same response. Okay? Alright. So now that we've done that, let's get this. Come on. We know that. Alright, now we're going to talk about this, quickly talk about the standard deviation of a discrete random variable. That is the sum of the probabilities minus the mean squared. And then you take the square root of that. I'm never going to ask you for that. Project 3 does not assess this. But when we're talking about mean, we have to talk about standard deviation. So if we wanted to find the standard deviation, we would take the expected value and then we would find the variance. We don't need to do that. So now we're going to talk about continuous random variables and the normal probability distribution. So we're going to talk about continuous distributions as represented by an area under the curve, and that area being equal to 1. So when we talk about the curve, we are talking about the bell curve. Come on. Pen. In color. Black. Thank you. Let me draw this. And let me draw this. So when we're talking about the curve, we're talking about the bell curve. That's the best bell curve that I could possibly draw. Okay? And this area is equal to 1. Now, if you stick with me, you're going to figure out how to use z-scores to get areas and probabilities from that. Now, when I talk about, I use area. I use the words area and probability. Oh, dyslexia. Let me erase that. Erase the link on the slide. Let me try again. No, I don't want a highlighter. Pen. Probability and area. They are probability. They are equal words. They are interchangeable words. When I talk about area, I'm talking about the probability of something that's going to happen. So we have our bell curve. The area equals 1. If I wanted to find the probability of something between something, that is the area between the two somethings. We're going to get into this in depth in the next half of this video. And then we're going to look at some examples. So, properties to know about the normal density curve or the normal curve. We know it's symmetric about the mean. The highest point is the mean. There are inflection points at the mean plus or minus standard deviations. Inflection points are where the curvature of the graph changes, and the graph never touches the x-axis. So what does that all mean? So this and this bar should be a little bit further out. So if we broke this up by our mean and our standard deviation of the population, 68% of our data is going to lie in between the first two standard deviations. And then 95% of the data lies within 2 standard deviations of this mean. And then 99.7% of the data lies within 3 standard deviations of the mean. Okay? So what does that mean? So standard normal distribution, we can standardize, and we have our x value minus our mean divided by our standard deviation. We can use the bell curve and z-scores to determine the probability of an event occurring. There's a chart in the book that helps us do that. We also have a chart in our resources folder in Plato, I believe. If not, there will be one at some point in the ether, in the future. So let's look at an example. So we have, this is from the 2nd edition trading volume. The Associated Press reports that a mean trading volume for equity and index options contracts was 3.6 million in July of 2007. Assume the distribution is normal with a mean of 3.6 in millions and a standard deviation of 0.5 in millions. Find the probability that a randomly selected day of trading has the following volume: more than 4.1 million contracts, less than 4.1 million contracts, and between 3.6 and 4.1 million contracts. So the first thing we should do is we should visualize what we're looking for. I do not want to be in color black, yes. So the first one, I'm going to draw a bell curve. I have a mean. The mean was 3.6. I first want to know the area under 4.1. So I want to know the probability that something will be in area 4.1. Okay, below 4.1. Then I want to find out above 4.1. So I want this area. Then I want to find in between a certain amount. So it was between 3.6 and 4.1 million. So let me erase some of that. I screwed that up. So we got the mean at 3.6, and then we're over here at 4.1 when we want to find the in-between. The first step of doing this is finding the z's. Okay? So I got to find the z for 3.6 and 4.1. So for the z for 3.6 is going to be 0. And the z for 4.1. So let's find the z for 4.1. Minus 3.6 divided by 0.5. Let me get that calculator out. I don't need the history. Why are you showing me the history now? Standard calculator. Scientific. Okay. Ooh, I have a graphing calculator? Since when? That's awesome. All right, sorry. Learning new things. Standard. All right, I need 4.1 minus 3.6 divided by 0.5. And that gives me a z-score of 1. Okay. So my z is 1. Can't believe I needed a calculator for that, but I did. Okay. So with a z of 1, we want to find more than 4.1 million contracts, less than 4.1 million contracts, and between 3.6 and 4.1 million contracts. So I'm going to pause the recording real quick and get a chart up. Now in your article reader, you have this table, the standard normal cumulative proportions. Okay, so we're going to look for a z-score of 1. So we go to table Z and we look for 1. And 0.0 is 0.8413. So if we were looking at, let me put this back up. This area right here, in color black. This area right here is associated with 0.8413 probability. So that means that this area is 1 minus 0.8413, which becomes 0.16 something. So about 0.16. And then we can subtract the 0.84 and the 0.16 and get the probability here. No. I'm a liar. We would take, this right here is the 0.84. And we know that this right here, highlighter in it, this right here is all 0.5. So, because it's half. This is 0.5 because it's half. So we have a 0.34% chance, not percent chance, but 0.34 probability that we would make 3.6 and between 3.6 and 4.1 million units. Okay, let's look at the next example. The mean wind speed in San Francisco is 13.6 miles per hour in July, according to the U.S. National Oceanic and Atmospheric Administration. Suppose that the distribution of the wind speed in July is San Francisco is normal, which means it follows the normal curve, with the mean being 13.6 and a standard deviation of 6. Find the probability that a randomly chosen day in July has the following wind speeds: 7.2 miles per hour or less, greater than 25 miles per hour, between 15 and 20 miles per hour. Now, an actual application here is tours to Alcatraz Island are canceled if the day is too windy, specifically if the wind speed is higher than 99% of all other wind speeds in July. Find the cutoff wind speed. Suppose that a particular day in July has no wind at all. Should this be considered unusual? On what do you base your answer? Do I want to make this video 30 minutes long? Yes, we're going for it. Sorry, guys. We're already in deep. I'm not cutting it off. We'll just get this done. All right. So, we know that the mean... Oh, we'll just deal with that marker there. We'll deal with pen and color. So, we know the mean is 13.6. We know the standard deviation is 6. We want to find 7.2 miles per hour or less. So, we know we're at 13.6. We want to find 7.2 or less. So, we're looking at this probability. Now, I'm going to end up using Excel to find some of these. There is a way that there's a code for Excel to do this stuff for you. So I will show you that instead of using the chart for this problem. So we're looking at 7.2. So we got Z equals X minus mu over the standard deviation. So let's find the Z for 7.2. So we've got 7.2 minus 13.6 divided by 6. And that gives me 1.07. So negative 1.07. All right. So to the Excel. We're going to give ourselves a new sheet here. All right. For this, I'm going to type in equals. And I'm going to go norm.dist x, which is the 7.2. The mean, which is 13.6. And the standard deviation is 6. We are looking at a true probability mass function. We want false. No. Cumulative distribution function. Yes. We want cumulative distribution. So we're going to go true. So we have a 0.14. So the area here is 0.14 or 0.14 probability or a 14% chance of that happening. Greater than 20 miles per hour. So we want greater than 20. So we have 13.6 right here. 20 is like over here, and we want this area. So to find that area first, we got to find the z-score for the 20. And that will give us gives me 1.07 again on the other side. So to the Excel equals norm.dist x 20 13.6 6 true. Now that's going to give me everything up until 20. I need to go equals 1 minus this guy, and that gives me a 14% chance on this side as well. Now, because these are symmetric, and I know that, okay, I know that because the z-scores were the same, just on opposite sides of the mean. Now, I want to find between 15 and 20. So I now need to find 15. So we got our mean at 13.6. We got 15 and 20. So we want to find this area. We already know that 20 itself is 85.85 something. So then we got to find it for 15. So I'm going to get Excel open again. And we're going to go equals NORM.dist for 15. Mean is 13.6. Standard deviation is 6. We are looking at true. And that gives me about 60%. But that is for 15. So now we got to take equals the 20 minus the 15. And that gives me about 26%. So my answer for here is 0.26. What else did I say? 0.2647. 0.2647. Okay? Now, rest of the application. Says tours to Alcatraz Island are canceled if the day is too windy. Specifically, if the wind speed is higher than 99% of all other wind speeds in July. Find the cutoff wind speed. So I need to look here. And here's my 13.6. I want to find something that's associated with an area of 0.99. So I need to go back into Excel. And then I have to go equals NORM.INV. Probability 0.99. Mean 13.6. Standard deviation 0.6. No, just 6, not 0.6. And that gives me a cutoff of 27 miles an hour. All right. 0. Is 0 unusual? To find that out, Z equals 0 minus 13.6 divided by 6 equals. We can figure that out just by our Z-score. And we got 13.6 divided by 6. That's 2.27. 2.27. That's a negative 2.27. That is not unusual. It is not smaller than negative 3. Okay? So, thank you for coming along on this wild half an hour long ride. I try and keep my videos shorter than this, but today that just didn't happen. So thank you for your time, and I hope that this answered all your questions. Have a great day.